Welcome. We want to look on the eigenvalues and eigenvectors of matrices. Yes, the eigenvalues and the eigenvectors. So we start by the definition. For equations such as those of coupled oscillations and vibrations, they bear the form x equals to lambda x. So here A is a square matrix represented as AJ. X is a column matrix represented as XJ, and lambda is a scalar quantity which can be a number. So for non-trivial solutions, that is the condition when x is not 0, the values of lambda are called the eigenvalues of matrix A. And so the corresponding solutions of the given equation Ax equals to lambda x are the eigenvectors of matrix A. Let's say we have the set of equations below. Yeah. So if we simplify this expression, we will have, so first, from our initial equation, we solve. So this is what we have. But remember, we said that lambda is a scalar quantity and A is a matrix. So for us to make this lambda to be subtracted from A, we have to make it a matrix. And so that is now by multiplying it with an identity matrix. So we write, it becomes in this form. So expressing this equation in this form becomes in this form. So back to our equation, we say for this set of homogeneous linear equations to have non-trivial solutions, one condition must be met, and that condition is that the determinant of this matrix A minus lambda should be 0, and that is this matrix. So here, this one is called characteristic determinant, and this equation is called characteristic equation. So we are going to look at examples, first starting from a 2 by 2 matrix, then a 3 by 3 matrix. So let us see. So we want to determine the eigenvalues and eigenvectors of Ax equals to lambda x, where A is a 2 by 2 matrix of this form. So first we write our characteristic equation, and here is it. So our characteristic equation is here. So substituting A in this form, we have this form. So solving, we obtain the expression. So expanding this quadratic expression, we have so using the method of factorization, we obtain, so we get our values of lambda to be -1 and 8. So now these are the eigenvalues. So these are the values we are going to use to have or to find the eigenvectors. So from our equation, we are going to substitute the values of lambda for us to obtain the eigenvectors. So we have, so for the first value of lambda 1, this is not the equation we have. So when we solve it, we have, so since the ratios of this equation are the same, we just take one equation, so just take the second one. So by solving, we find the ratios of x1 and x2, and then we write them in this form. This is now our first eigenvector. It can be presented in form where alpha is a scalar quantity or a number. So here we can say let alpha be 1. So this is our first eigenvector. So by taking the second eigenvalue, we also follow the same procedure. So we start by substituting the value of lambda here. So we also solve the equation to have, so the ratios are also the same. So we take one of the equation, and so we obtain, so then we present our second eigenvector in the form. So by taking the value of alpha to be 1, so we obtain our second eigenvector as so these are values, right? So we want now to look at a 3 by 3 matrix. Yes, so see this example. Determine the eigenvalues and eigenfactors of ax equals to lambda x, where A is this matrix. So the first step is for us to write the characteristic equation. So we want to calculate the determinant of this matrix. So by factorizing 2 minus lambda, we have, so by this we obtain our first eigenvalue as 2, and so we open this bracket. So by factorizing this quadratic equation, we obtain our values as, so we are going to substitute these values in our equation to obtain the eigenvectors. So we start by the first eigenvalue. So this is the form. So by solving this equation, we have, so we write these equations as, so solving this first equation, we have, so x3 equals to a quad of x1. So substituting this value of x3 here, we have, so putting right terms together, we obtain, so therefore x2, so yeah, writing the ratios of these values, we have, so that is to say this 4 to 1. So by this we obtain our first eigenvector as, so we proceed to the second eigenvector, and that is by substituting the second eigenvalue in the equation. So we proceed, we substitute this form, so we solve it as, okay, so now we write the equations as, So by substituting the value of x2 and x3 here, we find. So from this point we can be able to obtain our ratio as 1 to 0. So the ratio is, and so our second eigenvector becomes. So we proceed to the third eigenvector, where we will find it by replacing or substituting the third eigenvalue in the equation. So we solve it and we obtain. So then here we also write the individual equations as. So the second equation is, so that means and also the third equation is, so by substituting x2 here, which is 0, becomes, so our ratio now becomes 0 to, so it becomes 2 to 0 to 3. So our third eigenvector is written as. So that's how we obtain the eigenvalues, the eigenvectors of matrices. Thank you for watching. Consider subscribing to our channel for more videos.